Welcome back. This is week 9 of inverse methods in heat transfer. In the last couple of videos, we saw binary classification, which meant that if you have some category which needs to be split into two, let's say cancer versus no cancer, that would be the case of a binary classification problem. Now we are going to extend that here into a multi-class classification case. So here you have more than two categories that you can split the data into. So let's say the number of categories is k, so then k is greater than 2. For example, you have an image and this image is of something. If there were only two categories, typically you will use a binary classification approach. But here, if it's, let's say, a cat or a dog or a horse, then the number of categories is 3. Similarly, you could have something like laminar, turbulent versus unknown. Okay, so that could be a possible 3-class classification problem. Or you could have many more cases. For example, laminar, turbulent versus transition. So this would be the example of k equal to 3 classes. In an image, you would see something of this sort in case it's a binary classification problem. In case we are putting all the data at one place, they could cluster in a certain fashion, which would make it appear that you have 3 classes where you want boundaries. Okay. Now, in all the problems that we have done so far, I have made a certain implicit assumption, and I'll deal with this a little bit later, but you would have classes of this sort. And you can see that you can now draw boundaries that separate, let's say, the k equal to 1 from the k equal to 2 and the k equal to 3 case. Okay. Now, how do we do this? Here, we don't have just a single decision boundary, but effectively you have 2 decision boundaries, or in some cases, you can even visualize this as if it has 3 decision boundaries. So how do we find that out? So once again, we go back to our old idea about machine learning essentially being a combination of these 4 ideas: data representation and data set, what the forward model is, what the loss function is, and what the optimization algorithm is. So what is it for the multi-class classification problem? So in case you have a multi-class problem, it turns out that in data set, just like last time we did a scalar representation, y equal to 0 or 1, there is something called a one-hot vector representation that we'll have to use. The forward model will be very similar. We'll have linear, but we won't have sigmoid at the end. We will have something called a softmax at the end. The loss function is what is known as a categorical cross-entropy loss function. And the optimization algorithm stays as gradient descent. Just as before, if you have lots of data, you can use stochastic gradient descent or mini batch gradient descent. Otherwise, we are still happy with just batch gradient descent. So let's look at these 3 alone within this video, and the rest of the details actually exactly happen to be exactly the same as before. So first, let's start with data representation. So the representation has the following problem. Okay, so let's take this simple example. You have an image. Again, let's say I have a 60 cross 60 image, which means there are effectively 3,600 inputs which go here. So if I write 1 and I unroll it, I will have to write till x 3600 here. Okay. I put all that together, and how do I get that? I simply get it by unrolling, as I have said multiple times before. I can unroll this and just write it out in one single row vector, one single column vector. There are other ways of doing it, but we are not discussing that in this case. Okay, so X representation is straightforward. Again, it's as usual. Now comes the representation of Y. Let's say this image, which is an image of something, it's already given to you. That's the image of a cat or a dog or a horse, and you just need to figure out what it is. Now you have 3 classes. Y is either a cat, or it's a dog, or it's a horse. Now, how do you represent it? Now, suppose one option is I say cat is 1, dog is 2, and horse is 3. This is problematic because remember, when we had just 0 or 1, we could simply make up a function that went from 0 to 1. But it's very hard to do this between 1 and 3. So we will need to think of something else. We might think of other possibilities such as -1, 0, 1. And even these don't work well because we have to map the space between this and the space between this. And we like the fact that we had a 0 to 1 and there was an interpretation as probability in the binary case. So people came up with a clever solution. Now, instead of this being a scalar, that is, notice here y is just one single number. This is also a scalar. We start representing y as a vector. Okay. So y is represented as a vector as follows. Y has 3 components. I'm going to write it as a row just because it's a little bit more spatially efficient. So y1, y2, y3. Okay. So this is what it represents. This will say whether it's a cat or not. This will say whether it's a dog or not. And this will say whether it's a horse or not. Typically, for an actual image, if it is a cat, then y will look like 1, 0, 0. If it's a dog, if it's a dog, y will look like 0, 1, 0. And if it is a horse, it will look like 0, 0, 1. This representation, notice, is a vector representation and it's called a one-hot representation. Whatever we did for logistic regression was a binary representation. This one is a one-hot representation. Why is it one-hot? Only one of these is active at any point. So you can imagine a switchboard with just 3 bulbs and one of them will light up. If the first one lights up, I'll say cat. If the second one lights up, I say dog. And if the third one lights up, I say horse. And only one of them will be lit up at any instant of time. So this is a simple one-hot representation. But our problem doesn't end here. We have a problem of finding out, but what about y hat? Remember, y hat could be any number between 0 and 1 when we dealt with binary classification. So here too, we can now think of a y hat. Let's take an example y hat. Let's say we put the constraint that all 3 numbers, all y hat I, have to lie between 0 and 1. Okay. So if we do that, let's take an example. I'll say y hat, this one is 0.1, this is 0.3, and this one is 0.6. Can we interpret this? Actually, it turns out there's a very natural interpretation. This says probability that this x is a cat is 0.1. Another way of saying it is probability that y1 equal to 1 is 0.1. Okay, remember y1 is just the first component. Okay, this one is probability that this is a dog is 0.3 and probability that this is a horse is 0.6. Since the greatest probability occurs for a horse, we would most probably we'll classify this as a horse, but we'll say it's a horse with 60% probability. So this is a very simple representation. Now notice again, I am emphasizing this. This was represented as a vector. Okay, even though there is one quantity, it was represented as a vector of size 3. And what happens with words? Let's say we want to find out text and we have email and something like, okay, I will give you money. Okay, is some text that is sitting in an email. And I want this as a vector. Now, the way we do it is each word finds its dictionary place, but the entire dictionary is a one-hot vector. Okay, so you give a vocabulary or a vector of size. Let's say there are 100,000 words in a dictionary, for example, so 10 power 5, that many circles we have here, and let's say I is the 50th thousand word, then that alone will be 1, and the rest of the all the entries within this vector will be 0. So each word is then represented as a vector of the same size, of 100,000 size, but it will be a one hot vector. So this will be a sequence of one hot vectors, and only one of them will be 1. Okay. So this is a very complicated way of doing things, but nonetheless, it's complicated at least for dictionary words or sentences, but for images, it's fairly straightforward. You just have as many entries as you have classes. So the size of y hat is exactly equal to the number of classes. So you have y1, y2, y3 up till yk, or y hat 1, y hat 2 up till y hat k. Okay. So that's it for the representation. This is simply a one hot representation. The next question was that of the forward model. Okay, so let's make the forward model again in this case of having 3 entries. So for the sake of argument, let's say I have an input with 4 neurons and I have 3 neurons at the output. Okay. From here, I want to take out y hat 1. From here, I want to take out y hat 2. And from here, y hat 3. That's the probability that this is a cat, probability that this is a horse, probability that this is a cat, a dog, and this is a horse. Okay. Now, how do I make my weights and models in this case? So the way we do it is this. Of course, I'll connect this. This is what is known as fully connected. So we'll put some weights here. We'll say W1, W2, W3, W4. All right. Then in this neuron, there'll be first a summation, which basically means W1, X1 plus W2, X2. So let's say this is X1, X2, etc. up till X4 plus W3, X3 plus W4, X4. But after that, you also want a non-linearity. So this, of course, is Z, is this linear combination. So Z is, as usual, sigma of Wi xi. But then the output, which I am calling y hat, or we typically call A1, the first activation, is some non-linearity of Z. So G of Z1. Z1 is the linear output here. Now, what about the second case? In the second case, I join these. Now, here is a problem. If I call this W1, W2, W3, W4, I'll have confusion between which W1, W2, W3, W4 it is. So I will call this W11, W21, W31, W41. I'm going to change the notation within the next week. But this is just to make clear that there are 4 weights, these 4 weights for the first neuron. Similarly, another set of 4 weights for the second neuron. Now, what can we call them? Instead of calling them W11, we'll call them W12, W22, W32, and W42. Okay. Similarly, we have the third neuron. Now you can see that it gets fairly messy, but nonetheless, this is really how real neural networks look pictorially. Okay, so this is W13, W23, W33, and W43. So suppose I want Y3 hat, this quantity here, Y3 hat, we would say is a non-linear function applied on the linear activation, which was Z3. Whereas Z3 itself, which comes here, is from a linear combination of these 4. So Z3 would be W13 X1 plus W23 X2 plus W33 X3 plus W43X4. Okay. So that's it. It's a simple model. It is just a logical extension of the binary classification or the logistic regression model. All we did really is just add more neurons at the output and just go with that. However, we still have to figure out what is Z, or sorry, what is G. Now, we might think we can use sigmoid. Okay. Can we use sigmoid? If we use sigmoid, the positive thing is y hat 1 would lie between 0, 1, y hat 2 would also lie between 0, 1, so would y hat 3. But there is a problem. Okay. The problem is y1 hat plus y2 hat plus y3 hat should always be 1. Why do we want it to be 1? Because we want to interpret it as a probability. Notice this here. If the probability that it's a cat is 0.1 and the probability that a dog is it's 0.3, the probability that it's a horse should be 0.6, because the sum of these three should add up to 1, because these are the only three possibilities that exist. On the other hand, if it is just sigmoid, this could be 0.5, this could be 0.5, this could be 0.5, and we would no longer be able to interpret it the way we want. So we create a new function called Softmax. So Softmax is this. Softmax works like this. So suppose I want y hat 1. I will say it is e power z1 divided by e power z1 plus e power z2 plus e power z3. Y hat 2 is e power z2 by the same thing. I'll call this denominator. And y hat 3 is e power z3 by this denominator. And then obviously, if I sum the three, I simply get 1. This is the advantage of creating this softmax function. It has one other nice advantage, which I'll talk about the next week. But the advantage of the softmax function is that we are always ensured that we can interpret the output as if it is a probability. So what we have looked at up until now is that the data is represented as a one-hot vector, and the forward model is exactly the same as the logistic regression model, except we use softmax instead of sigmoid. Now, I must point out here, and I will do so once more when we come to the next week, that this softmax only needs to be used at the end when you want to find out just the output. If suppose there is a calculation in the middle, you can actually use sigmoid there. But anyway, these are greater details when we come to neural networks, and I will discuss that in the next week. The third part is the question of the loss function. Now, what is the loss function here? Now, I'll write the loss function, but it should also satisfy the same property that we wanted for our binary cross-entropy loss function. So I'm going to call this JCCE, standing for categorical cross-entropy loss function. And the purpose of this loss function is exactly the same as the previous one. And strangely enough, it looks simpler than a binary cross-entropy loss function. It's like this. It's minus sigma of yi ln yi hat. That's it. I equal to 1 to k. This looks really simple. All it is, let's say I have some example like, again, I'll say 0, 0.1. Actually, let me make this a little bit better. Let's say y hat is 0.2, 0.3, 0.5, and the actual ground truth is 1, 0, 0. Let's say we actually have a misclassification. Okay. So we have misclassification in that the one which seems to be most probable due to your model is 0.5, but the actual truth is that it is a cat. Then we would calculate this in the following way. This will be minus y1 times ln y1 hat minus y2 times ln y2 hat minus y3 times ln y3 hat. Now notice y1 is 1. Okay, so this one will be minus 1 times ln 0.2. You can calculate this. Now minus 0 minus 0. So this is simply minus ln of 0.2. So that is the loss function in this case. Now I'm going to argue that even though it looks less complicated, it is almost exactly the same as the binary cross entropy. So we can compare this with the binary cross entropy case. Now remember, in the binary cross entropy case, we had just two classes. Y was either 0 or 1. Now this was the scalar representation. Now instead, if we represent this also as a one-hot vector, now instead of calling it class 0, I would have called it 1, 0, because there are two classes and it's the first class. And instead of calling it 1, I would have called it 0, 1. Okay. So let's say this is y1, the first component of y. This is y2. So in the case of class 0, or in the first class, I would say y1 is 1 and y2 is 0. The second case, y1 is 0 and y2 is 1. Similarly, if I look at y hat would look something like 0.2 and 0.8. Okay, so this one would be y1 hat and y2 hat. All right. Okay, putting this together, if I actually calculate the cross entropy loss function here, that should be minus y1 times ln y1 hat minus y2 times ln y2 hat. Now we know that y1 is always 1 minus y2 because there are only two classes. So if y1 is 1, then y2 has to be 0. If y1 is 0, then y2 has to be 1. Similarly, we also know that y1 hat will be 1 minus y2 hat. So substituting this will give us 1 minus y1 hat, 1 minus y2 times ln 1 minus y2 hat minus y2 ln y2 hat, which is exactly the same as J binary cross entropy. So you see the terms y times ln y hat and 1 minus y times ln 1 minus y hat. So what this shows is that what I have as the categorical cross entropy loss function is exactly the same as the binary cross entropy loss function, except it has been extended to higher number of classes. What do we do finally about the final portion of the puzzle, which is the optimization algorithm? We simply use, again, we use gradient descent. Now it might seem like, okay, all this is fine, but how do we do an actual practical case? So we will come to that next week. But all I wish to point out is it is actually fairly straightforward. We don't do anything different. So if I go back to this image here, okay, so let's say this has about 30 points here. I just collect these 30 points. I find the x location, the y location, or x1 and x2. x1, x2 class represented as a binary, as a one-hot vector. So this is the way you will write it. So let's say the first point is 0.3, 0.4. And this belongs to class 1, so this will be 1, 0, 0. The second point is, let's say, 0.1, 0.7, and this belongs to, let's say, 0, 1, 0. So you will note this down, and you have a model. Your model is like this. Okay, it's a more complicated model, but you simply can write down y1 hat in terms of all this, y2 hat in terms of all this, and y3 hat in terms of all this. That's your forward model. Then to do back propagation, you have to do W equal to W minus alpha times del J del W. Now, how do I calculate del J del W? This I will talk about next week. I'll just give you the expression directly in the next week. But keep on iterating, and finally you will get the weights so that magically you will actually get a nice classification boundary. So we will look at a couple of toy problems in the next week for both logistic regression as well as, well, most probably not multi-class regression, but for logistic regression, definitely we'll look at an example in the next week, and we will move on to neural networks. But before we move on to neural networks, there would be a question. Why exactly do we even need neural networks? And that I will answer in the next video. Thank you.